Okay, welcome everyone. So today we are sort of officially past the halfway mark in the course. And today I wanted to take some time and I wanted to go over the midterm problems as well as some of the problems from the homeworks on which the students did not do as well as other problems. Okay, so so first of all, yeah, even before we start getting into problems, from next week we will sort of start the part 2 of the course. So this course is roughly structured into two different parts. The first part focuses on sort of basic foundations, proofs of security, how to write proofs of security, definitions of very basic and fundamental primitives like encryption, signature, and so on. The second part is more about how to use these primitives in a bigger system, like we will look at blockchains, zero knowledge proofs, and secure multi-party computation. So the first part is more about building the foundation, and the second part is making sort of your building taller and taller. So in the first part, a big component of the course was doing proofs of security and doing proofs of security in the right way. So that is always sort of the more tricky part of the course, because you might have realized that uh, you know you can do proofs of security, but many students, they are not sure whether they have done this proof correctly, or is there something missing or something like that. So rest assured, that is not unique to you. Crypto proofs of security, they are sort of very tricky, and it takes a while to sort of get a hang of what you need to do, and what all are the exact steps required. So it's great. So we are past that part of the course, and um, you know in the second half we focus more on the big ideas rather than the subtle things which people tend to miss. Okay, so let's go over the midterm problems. Actually, one common mistake which the TA pointed out, and they asked me to sort of talk about it, is suppose you write some probability of something to be greater than negligible. So what does this mean? This doesn't mean that the probability automatically becomes noticeable. This just means that there exists this negligible function such that your probability is greater than this negligible function. But it is still possible that this probability is sort of still less than or equal to another negligible function, negligible prime n. So when we write this negligible of n, it just denotes some negligible function. So these two statements are entirely possible together. So if you want to say that something is noticeable, it is not sufficient to write something like this. Rather, you should explicitly write greater than or equal to some noticeable here. Okay, so this is just how to write things correctly. We are not deducting any points for this, but make sure that that you use the right language in future. Okay, so let's start with the first problem. Let me remind you what the problem was. So in the first problem, you have Alice. Alice has hired you as a consultant. Alice is the president of a large company having, let's say, hundreds of employees. And Alice would like to send secure encrypted emails to each of them. Okay. And the idea is that Alice only has a mobile device, so she cannot really store 100 different keys on the mobile device, one for each employee, but rather she can actually remember the email ID of each of her employees, right? And yeah, you have to design a solution which sort of only uses very small storage to store all the keys, right? So clearly, Alice cannot sort of generate 100 different random keys and expect to sort of compress them and store some small part of that. So that's not going to work, but rather what you have to do is you have to use pseudo randomness here rather than random keys. So one option is to use a PRG. Alice just stores a PRG seed, and PRG allows you to expand a small seed into a large seed, into a large random looking string. But PRG, it's not clear how to use it, right? Because if you want to use PRG, Alice also has to remember, which part of the output to use for which employee. And looking at the email ID, that's not some information which you can readily derive. So PRG doesn't really work correctly. The correct solution here is to use a PRF. Okay. So Alice stores PRF seed, or let's call it key. Okay. And the key for email ID, this ID, is derived as the PRF output on K, comma, this email ID. Okay. Alice just has to store this single secret key K, and you invoke the PRF on that. The second input would be the email ID. All the email IDs are unique, so all the keys which you would end up using would be sort of pseudo random. And then you can use any encryption scheme of your choice, AES, Algomal, or whatever. Algomal is actually public key, AES, or any symmetric key encryption scheme you can use. Okay.
Sir, I had a small doubt in this question.
Yeah.
So while doing this question, I also thought the same thing. So I specifically did not take PRF because it is not given that the email IDs are part of the group, and it can happen that two email IDs, like when you take modulus, you can like they map to the same element of a group, and that's why like, and for PRG what you can do is you can alphabetically sort the email IDs, and then like the first email ID. So like say you have T employees, you generate a big
But
string
wait,
of
first
T.
of all, for the PRF,
Yes.
it doesn't need to be part of any group. The construction of PRF, which we saw in the class, that was for arbitrary strings.
Okay, maybe, okay, fine. Sorry, but for for PRG, like you can alphabetically sort the email IDs, and so for example, if your key length, the output, the key length that you need for one employee is K, you generate a PRG of, and you have T employees, you generate K into T length, and you alphabetically sort your email IDs, and the first K goes to the first, the second goes to the second,
Yeah, so
and
I
the
think
third goes to.
yeah, we will give some partial marks to that solution. But the problem is, if you want to alphabetically sort, right?
Yeah.
It's not clear that you can do it entirely in your head. You have to write all the email IDs on a piece of paper or on the mobile
But sir,
device.
like if you have a PRF, then like you'll need a PRF whose second input is as large as the longest email ID, right?
Yeah, so you will have to use that. That's correct.
So I thought that that might or might not be possible because like the email IDs are string and like.
So in the class, we saw PRFs where the second input can be an arbitrarily large string.
Okay.
And in fact, if you are worried about that, you can even apply a collision resistant hash function to the email ID first, and then you will sort of get a fixed length output. So maybe that solution is even better, but even if you write the solution, you will get full marks. Yeah, the problem with sorting is that then you are making an additional assumption. You're assuming that Alice not only can remember the email ID, but also remember the index where that email ID occurs in the whole list. So that may or may not be a reasonable assumption. At least the question doesn't say that. You can make this assumption.
But like I thought the question was basically on the point of the storage of keys. Like you don't want to limit the storage of the keys itself, like the email ID related storage, like it is in the head. Okay, I understand. Thank you. Thank you.
How
Any other
rigorous a
questions?
proof of security for this did we expect? Oh wait, is someone just having a hand?
Yeah, so proof of security for this. So
Like
even
it
if you
feels
write
pretty clear.
even if you write a couple of lines saying that all the email IDs are unique, and hence you are invoking the PRF on different inputs, which means that the PRF output looks like a random function. That's good enough. But in the midterm, we are sort of more liberal about grading. So we don't really expect you to show all the hybrids here. Any other questions? Okay, so let's look at the second problem. So second problem is F is a PRF and you are given a secret key encryption scheme. So secret key encryption scheme looks something like the following. Ciphertext is M XOR F of K and a string of zeros. And you are asked, is this a good, I missed, there's a question in the chat. We assume randomly sampled key in security of symmetric key. Is it an issue with the output of the PRF is pseudo random? No, it is not. So, I mean, if you want to write down the full proof, there will be hybrid where you switch from using PRF to a truly random function. And once you are using a truly random function, then all your keys are really random, coming from the right distribution. Okay, going back to question 2. So this is how your ciphertext is generated, right? And here you are XORing the message with the output of the PRF on an all zero string. Well, output of the PRF on any string looks essentially uniform or indistinguishable from uniform. So this is very similar to using a one-time pad. So this is secure. This is part A. And part B is asking, is the above secret key encryption scheme multi-message secure? And the answer to that is clearly no, because you are using the same key. If I was putting the message here or some sort of random string as opposed to a string of all zero, then maybe we can talk about multi-message security. But I have the same key, I have the same string of zeros. So every time I'm XORing with the same thing. And this is analogous to using a one-time pad where you use the same secret key multiple times, and this is clearly not secure, right? I can, for example, take two different ciphertexts. I can XOR them. The keys will cancel out, and I'll get just XOR of two different messages, which already reveals some information about these two messages. So no, going to multi-message security. Okay, I hope this is clear. So let's move on to problem 3, which was only for the master's and PhD section. So problem 3 gives you a large number of distributions. Any two distributions, two subsequent distributions, they differ very little. They differ in only like only in the beginning and the end, just two strings. So any two consecutive distributions, they are actually very close, computationally indistinguishable. In fact, they are statistically indistinguishable. But when you look at the first distribution and the last distribution, they actually clearly look very different. It's easy to distinguish these two distributions. So what is going on? Well, the problem here is that there's an exponential number of hybrids. The number of distributions is exponential. It's actually 2 to the power n, I believe. Yeah. And even if two consecutive distributions are close to each other, yeah, when you sum them all up, it will be 2 to the power n times some negligible quantity, and this may or may not be noticeable. So at least the usual hybrid argument doesn't let you prove that first and the last distribution, they are indistinguishable. And this is where the proof breaks down. Okay. So let's look at question 4. This question is actually pretty interesting. So this question is essentially asking you to design what is known as a multiplicatively homomorphic encryption scheme. Okay, and the idea here, what the question is asking is, you are given several strings, several messages, S1 to Sn. You can encrypt each of them individually using a public key encryption scheme, and you store all the ciphertexts on the cloud. Okay, and you yourself store only the secret key, none of the ciphertexts and none of the messages. Okay, so we have these messages S1, S2 up to Sn, and from these, let's say you get ciphertext C1, C2 up to Cn. Okay, and now what you need is you would like to recover the multiplication of some subset of these messages. I is in A, where A is some subset. So how do you do that? Well, one option is you download all the ciphertexts from this subset. So clearly, cloud is just storing this. So one option is to download all the ciphertexts corresponding to this subset A. You decrypt each of them individually, and then you multiply the resulting messages. That would allow you to recover this quantity. But can we do something better, right? Can you have the cloud compute a single ciphertext such that you just decrypt this ciphertext and you recover this quantity? And the cloud doesn't have the secret key, or in fact doesn't have any secrets at all. Just cloud just stores the ciphertext. So here the best way to do it would be to use Algomal encryption. Okay, so if you use Algomal encryption, how does it work? Your secret key would be some, let's say X. Your public key would be G to the power X. Okay, and your ciphertext CI would be G to the power, let's say RI, comma, SI times G to the power XRI. Okay, let's also denote it as CI of 1 and CI of 2. So each ciphertext has these two different components. So the cloud is storing all these ciphertexts, and then what you can do is you can send this set A to the cloud, and cloud can just compute a ciphertext C, which is as follows. So that is just pi of I in A G to the power Ri, which is just so just the first component of the ciphertext from set A multiplied with each other, and I in A Si times G to the power X Ri. Okay. And now let's say denote R to be summation I in A Ri. Okay, then what is C? C is just, so when you multiply all these components, it translates to addition in the exponent. So you would just end up getting g to the power r, and then g to the power xr times okay. And in fact, let's even denote s to be the multiplication of all the messages in this set A. Then this is just S. Okay. So this is a valid Algomal encryption of just S. You don't need to do anything special to decrypt it. Okay. So server sends C to, who is the character, Alice or you? Okay. The server sends the ciphertext C to you. You have the secret key X, and you can just decrypt the ciphertext as any other Algomal ciphertext, and you can recover the message S, which is exactly what you want. Okay, so this shows that Algomal encryption has this property of being multiplicatively homomorphic. And there's this whole area of cryptography which is about designing different type of homomorphic encryption schemes. So actually RSA also turns out to be multiplicatively homomorphic, because in RSA the ciphertext, or rather textbook RSA, okay, textbook RSA, which is not secure, by the way, but the ciphertext in textbook RSA is also just Si to the power E, where E is the public key, right? So if you multiply all these different ciphertexts together, phi of I in A, Ci, that would be just okay, which is just S to the power E. And if you have D, you can again recover S as usual, right? But unfortunately, as we all know, textbook RSA is not secure, so this is not a valid secure public key encryption scheme. But many encryption schemes have this property. And there's also something which is known as fully homomorphic encryption. We will talk more about this maybe in the last class. Just denoted as FHE in short. So here I was able to take several ciphertexts having several messages. I was able to multiply these messages. Can you add messages? Turns out in Algomal we don't know how to add messages, right? If I'm able to come up with an encryption scheme which allows me to multiply messages as well as add messages, I actually get an encryption scheme which allows me to sort of evaluate a whole circuit having addition gates and multiplication gates. These are known as arithmetic circuits, right? So addition and multiplication, if you get them together, that's very powerful. You can evaluate any arithmetic circuit. Coming to Boolean circuits, let's say I give you an encryption scheme which allows you to sort of NAND two values. Okay, and we know that NAND is actually the universal operator. It's the universal gate. If I give you the NAND gate, you can implement basically any circuit with the NAND gate, right? So the question is, can you design an encryption scheme which allows you to evaluate NAND gates? And the answer to that is yes. This is This is a scheme which was given by Craig Gentry in 2009. And that was the first ever fully homomorphic encryption scheme. We call it fully homomorphic because essentially given a bunch of ciphertexts, you can compute any function on these ciphertexts without having to decrypt these ciphertexts. And this is really powerful, right? So this means that I can just encrypt my data, send it to the server. Without decrypting the data, server will be able to do arbitrary computation on this encrypted data, return the result back to me in an encrypted form, and I can just decrypt it and I can get back the result, right? So think about it. This is like executing any program, a C program or a Python program. I can execute a Python program without having access to the input. I get encrypted inputs and I execute any arbitrary program on these inputs, and I can compute encrypted output. This is very useful in cloud computing and cloud security and so on. So anyway, we will not get to look at fully homomorphic encryption. That's pretty complex. It's based on something which is known as lattice-based cryptography. But even the simplest encryption schemes like Algomal have at least some homomorphism inbuilt inside them. Okay, so any questions before we move on? So now let's look at problem 5. So problem 5 is about designing a collision-resistant hash function family. So the description of the hash function is something like the following. You have the key generation procedure, or sorry, the procedure for generating the hash function. So here G is, you are given that the order of the group is Q and G is a generator of this group. So you sample H1, H2 up to HK, where Hi equals G to the power Ri, where Ri is sampled at random from ZQ. Okay, these are just random group elements. And this is basically the description of the hash function. And then how does this hash function work? Takes as input x, where x is interpreted as x0, x1 up to xk, and the output of the hash function is g to the power x0, h to the power x1, h1 to the power x1 times hk to the power xk. And you have to prove that the above hash function family is collision resistant, assuming the discrete log problem. Right, so we saw something like that in the class in one of the lectures, but we just had a single h there. We had G and we had h, so it sort of roughly had a compression factor of 2. Here we are building a hash function which has a compression factor of k plus 1. Okay, so let's try to solve this problem. So to prove that this is collision resistant, we will use contradiction, of course. So given an adversary A, which finds collisions, we build another PPT adversary B which takes as input y, where y equals g to the power r, and it outputs r with some noticeable probability. And this will be a contradiction, right? So note that here the adversary B has to choose the hash function, and B has a challenge. B has to solve the discrete log problem, and B has to embed the instance of the discrete log problem in the hash function. That's a very important step. I believe that some students sort of implicitly assume that they are given the hash function and somehow they have to solve the discrete log of one of the HIs. So that is unclear what you are doing in that case. So you always have to take as input the challenge, which is y, and then you have to compute the discrete log of y. Okay, so B works as follows. B chooses some j at random. And j will be from 1 to k, and sets hj equals y, which is equal to g to the power r. And for all other I such that I is not equal to j, B will sample Ri itself, so it knows Ri, and sets Hi equals g to the power Ri. Okay, so B knows all the exponents except this one. And let me highlight this. Okay, next is B invokes A on this description h1, h2 up to hk. Okay, then if A responds with, so suppose A responds with 2 inputs, x and x prime, such that this is the first input. First input is x0, x1 up to xk. It's not equal to x0 prime, x1 prime, and xk prime. Okay, so the adversary A finds a collision and gives us this pair of values. So these 2 inputs are not equal. On the other hand, the output of the hash function on these 2 inputs is the same, which means, but g to the power x0 times h1 to the power x1, hk to the power xk, this is actually equal to g to the power x0 prime, h1 x1 prime, hk xk prime. Okay, so A responds with inputs which satisfy this condition. So this also means that x0 plus r1 x1 plus rk xk is actually equal to x0 prime plus r1 x1 prime plus rk xk prime, and this is mod q because q is the order of the group, right? And here I am just using the fact that hi is equal to g to the power ri. So this value is equal to g to the power r1 x1, right? So I'm just taking the exponent of g and they should be equal mod q. Is this step clear? And now my claim is, let's call it claim 1. There exist at least two indices j, let's call them j1 and j2, such that x j1 is not equal to x j2 and x j1 prime, x j2 is not equal to x j2 prime. Actually, you don't even need two. You just need one index to be different here. And the idea is that if none of the indices is different, then then basically then
X equals x prime.
Sorry?
Then x equals x prime. You assume that to be false.
Yeah, then x equals x prime. And okay, yeah, the reason I need two indices to be different is because if just this is different from this, then I might fail. Okay, I need one of these to be different from one of these. That's what you need to prove. In fact, even in the previous construction which we saw in the class, we did something like that. Okay, and this is actually easy to see. If not, say only one index is different. Say only j1 is different. This would actually end up implying that rj1 xj1 is actually equal to rj1 xj1 prime mod q, and this also means that xj1 is actually equal to x prime j1 mod q, and this is by multiplied by inverse of rj1. Okay, inverse exists because q is a prime. So at least two indices are different, which means that one of the index must be here. One of the index, it implies that, say, j1 is not equal to 0. One of the indices is non-zero, we call that, let's say, j1. Now, what is the probability that j equals j1? So j is the location where I put my discrete log. And this is at least 1 by k. Okay, which is still noticeable. And if this happens, then Yeah, so in that case, I can actually compute Rj. And how do I compute Rj? Rj times xj minus x prime j would be some known value mod q. So now I'm just coming back to this equation. So in this equation, I know every single value except Rj. Okay, this is because Hj was y. I don't know the discrete log of Hj, which will be Rj. I know everything else. The remaining Ri's I chose on my own. I know all the xi's and xi primes. Okay, so I can take all the known values to one side and I'll be left with something like this. And now I have the fact that this is non-zero. So then I can compute Rj, and this is what my output would be. This would be the discrete log of y. And that's it. Yeah, good question and good answer. So at least 1 by, it could be greater than 1 by k because multiple indices might be different. Okay. Any other questions? So let's continue to the last problem. So in the last problem, you are given a pseudo random generator G with n-bit stretch. So it takes an n-bit input and gives you a 2n-bit output. You have to prove that G is also a one-way function. Why? Okay, let me see the questions. Where are we using the claim that two indices are different? Yeah, good question. So so note that here J is not equal to 0. So B was given some challenge Y, right? And B chooses some index J and sets Hj to be Y. J cannot be 0, right? There's no H0. H0 is the same as G. Okay. So this means that if only x0 was different from x0 prime, but all the other xi's were identical, then you never get to solve the discrete log problem, right? Because your chosen index is somewhere here, the randomly chosen index. On the other hand, if you have a guarantee that at least two are different, then one of them can be 0, but the other one has to be from one of these. Why is Rj a pre-image for Y? That's just by definition. We are setting Hj to be y. And Rj is the pre-image of Hj. This is equal to g to the power Rj. So by definition, Rj is the discrete log of Hj, not pre-image. Rj is the discrete log of Hj, and hence it is also the discrete log of y. Okay, pseudo-random generators. So you have to show that G is a one-way function. What is the intuition here? Why must G be a one-way function? So suppose I get the output of G, which is 2n bits, and I'm able to find an n-bit input, which leads to this 2n-bit string. That
you
means
can
the
assume
output
it came
is.
from the PRG. Yeah.
Sorry?
Then you can assume it came from the PRG
Yeah.
with very high probability.
Yeah. Then we know that string cannot be truly uniform. Okay, because you cannot compress a truly uniform 2n-bit string into an n-bit string. Okay, and let's try to do this a little more formally. Prove that G is a one-way function. So say you are given some PPD adversary A, which inverts G with some noticeable probability. Okay, then we will build B. To distinguish output of G from uniform. So what does B take as input? B takes as input some y, where y is a 2n-bit string. Okay, and B has to guess, is it the output of a PRG or is it a truly random string? Okay, so B works as follows. B invokes A on Y. Okay, now there are two cases. Say AY outputs X such that G of X equals Y, which means that A indeed successfully inverted. Then B outputs, the guess of B is just PRG. Else, what does B output? Else B outputs a random guess. Okay, with probability half, B guesses PRG. Probability half, B just says random. This is case 1. This is case 2. Okay. Now we are given that case 1 happens with noticeable probability. Okay, why? Because the adversary A does indeed invert with noticeable probability. And now my claim is, this claim will essentially complete the proof. In case 1, guess of B is correct with probability 1 minus, at least 1 minus negligible. Okay? And why? So if A successfully manages to invert, then actually the output must indeed be coming from the PRGG. And this is because if Y was a uniform 2n bit string, probability that there exists X such that G of X equals Y is actually negligible. And why is that? Because, there are 2 to the power n possibilities for Y, sorry, 2 to the power 2n, and there are 2 to the power n possibilities for X. These are different points. So very few values of Y, 2 to the power 2n minus 2 to the power n, values of Y have no preimage. They have no preimage with respect to X. You cannot invert them. Okay? So this means that if we are able to invert them, then the output is indeed the output of a PRG, except with negligible probability. Okay? So we have 2 cases. In case 2, we are winning with probability half. In case 1, we are winning with probability very close to 1. And case 1 happens with noticeable probability. So let me now skip the remaining sort of equations, but when you take the average overall of case 1 and case 2, your probability of winning would be half plus noticeable. Okay, any questions? We can do the probability calculations also if somebody is confused. So in general, this type of argument is used a lot in cryptography. In one of the cases, you are winning with probability half. In other case, you are winning with probability noticeably better than half. Doesn't need to be close to 1. Then the average of these 2 cases will also be noticeably better than half, as long as both of these cases occur with noticeable probability. Okay, so now let's move on to the homework 3. So in homework 3, I want to talk about primarily the third problem. In fact, the second problem as well, because they are connected. So in the second problem, you are given a one-time signature scheme, which is clearly insecure. But it's insecure in a very interesting way, which will help us also solve the third problem. So in the second problem, how do you sign? So maybe let's let's look at the problem first. So you want to sign n bit messages. In this problem, you just generate n random strings from the domain of f, input domain of f. And the secret key is sk is just x1 up to xn, and pk equals f of x1 up to f of xn. And how do you sign a message? So the signature just consists of signature sigma has xi if the ith bit of the message m equals 1. Okay. So you look at the places where the message is 0, and you want to include the corresponding xi's. So this is clearly insecure because, in particular, look at the all 0 message. The all 0 message has empty signature. And even without making any query, I as an adversary can always forge the signature on the all 0 message. Okay. Going further, in fact, given a signature on a message, let's say given a signature sigma on some message, message m, let's say the message is 0 1 1 1 0. Easy to compute sigma prime on any message m prime where m prime is obtained by changing some 1 bit to 0 bit in m. So essentially, I can take this message m. I can flip any 0 to 1. Sorry, I can flip any 1 to 0. And that only makes the signature shorter because I just have to take out that corresponding xi. Right? So given a signature on this message, for example, it's easy to compute a signature on 0 0 1. Rest of the message remains the same, or 0 0 0, and so on. Okay. So main thing to keep in mind is that it's easy to switch 1 to 0, but can you do it the other way around as well? Can you switch any 0 to 1? That you cannot do here. If you want to switch any 0 to 1, you will have to invert the one-way function because you don't have the corresponding pre-image of the one-way function. Yeah. Okay, so this is as far as problem 2 goes. And this also gives us an idea to solve the third problem. So in the third problem, we can increase the size of the secret key and size of the public key from n strings to n plus log n plus 1 string. Not all the way up to 2n. 2n is what we did in the class. But here we want to do something more efficient. Okay, and the idea is we modify the signing algorithm so given the message m, you define another message m prime, where m prime is m concatenation z of m, where z of m is equal to the number of zeros in m. Okay, you represent m as a bit string. And you concatenate the number of zeros. So what would be the size of z of m? My claim is that size of z of m is actually less than or equal to log n plus 1. Right? So if I have a 100-bit message, for example, then I need to represent a number which can be from 0 to 100, and that's just log 100, or log 100 plus 1. Okay, so now I have a message m prime whose size is n plus log n plus 1. And then I just use this previous scheme from question 2 to just sign this message. Okay, and even during verification, you have the message m, you can compute m prime, and you can verify the signature. Yeah, so it does not work if you count ones rather than zeros, and I'll go in more detail in the proof. Okay, so now let's say adversary is trying to forge the signature. And again, we are just trying to design a one-time signature scheme. Keep that in mind. So here we can consider two cases. So maybe let's try to do it by contradiction. Say adversary manages to forge, right? On some message, let's call this message now m1, which is not equal to m. Now we have two cases. Case 1 is m1 changes from 0 to 1 in m. So m1 is different from m, right? Which means that at least one of the bits is different, right? That bit could be you change 0 to 1 or you change 1 to 0. So let's look at case 1. At least at one position, m1 changes m from 0 to 1. At least at one index. Okay, but this is already a contradiction just from the scheme in problem 2 itself. The property that we observed in the scheme in problem 2 was you actually cannot change any 0 to 1, because then you need to include some pre-image in the signature, which you did not get as part of the signature on the message m. So we didn't even make use of our change in this case. What about the second case? Second case is m1 doesn't change doesn't change any bit from 0 to 1, but does the other way around. And one changes from 1 to 0. So this is the more interesting case, because this is exactly the problem that we were having in question 2. You can easily change from 1 to 0. But this actually implies that z of m1 is actually greater than z of m. Okay? I did not flip any 0 to 1, but I flipped somewhere 1 to 0. It means that overall I ended up increasing the number of zeros. So z of m1 is equal to z of m. Okay? Now, if this number is larger than this number, you represent both numbers as bit strings. This means that there must exist some index where z of m1 is 1, but z of m is 0. Okay, that's the only way z of m1 can be larger than z of m. But what does this mean? This means that now I look at the second part of the signature. Now in the second part, I have actually gone from 0 to 1. I have changed some 0 to 1, which again I cannot do in the scheme given in problem 2. And this is not the full proof of security. This is just the high level idea. Once you are able to prove that at least at one index in the overall signature of m prime, the adversary is changing some 0 to 1, then again you build an adversary to invert the one-way function by taking the image of the one-way function, putting it in one of the random locations, and hopefully that is the location which the adversary inverts. But here it's clear that adversary is actually inverting the one-way function, at least in one of the locations where adversary is going from 0 to 1. Okay. Should we move on to the second homework? So let me start with the second problem. So the second problem, you can make the Ddh assumption. The Ddh assumption says that g to the power a, g to the power b, g to the power ab is computationally indistinguishable from g to the power a, g to the power b, and g to the power r. And then you have some other distribution whose computational indistinguishability you need to prove. So for now, let's just start with the Ddh problem. G to the power b, g to the power ab is computationally indistinguishable from g to the power r. Okay, this implies that just for fun, I will add another random group element. This is just A2 is random. In both distributions. Okay, this really has nothing to do with anything else. So, these two are also computationally indistinguishable. Now, what do I do? G to the power a to b. So I replace b by a to b. G to the power ab. This is computationally indistinguishable from g to the power r, g to the power a2. Why is this the case? So first I added some random element, and then I started doing strange things with this a2. I put a2 here. So why does this step follow?
If you could distinguish the latter one, you could distinguish the former by just doing the multiplication and then using your distinguisher for the second.
Yeah, good. That's one way of looking at it. In fact, there's a direct lemma as well. If two distributions are computationally indistinguishable, you can apply any PPT function on these distributions, and the output would still continue to be computationally indistinguishable. So note that I am generating A2 myself. I can take this element and I can compute, given this, I can compute g to the power a to b myself. So that's what I do. Okay. In fact, let's start calling a1. So no difference. Just I'm renaming to make sure that we are getting closer to the final result. And let me just rearrange these g to the power a2, g to the power a, g to the power a1b, and then a2b. G to the power a to b. This is computationally indistinguishable from g to the power a1. I'm just changing the order. I'm not doing anything non-trivial. G to the power r. Let's call this r1. This question has r1 and r2. Yeah. Then g to the power a to b. Okay. Then finally, let's look at this. This is, I can apply the Ddh assumption again. Do I even need to do that? Here B is uniform. So I don't even need to apply the Ddh assumption again. B is uniform, B doesn't show up anywhere else. So I can also write it as g to the power r1 and g to the power r2. This is identical, the last step. So basically, I started with the Ddh assumption. I just need to add a bunch of random things and just rename. And this is what we need. This also proves that these are computationally indistinguishable. I think the third problem was fine. Yeah, in the fourth problem, I think many of you did well, but you did more work than required. So in the fourth problem, you are given two distributions, and then you are given two PPT algorithms, A and B, such that one of these algorithms distinguishes, and the other one just gives you a random answer. You don't know which one is which, right? And then you have to come up with a single algorithm which distinguishes. How do you do that? So I was just talking about how there's a general principle which we can use in a lot of different places. So let's design our algorithm as follows. So we have to design a PPT predictor C. Okay, C gets something as input. Then C flips a random coin and then picks either A or B. And then C just uses that one. Okay, with probability half, C will end up picking the right algorithm, which distinguishes with noticeable probability. With probability half, C picks the algorithm which gives you a random answer, right? But now both of these cases are happening with probability half. And in one of the cases, you are getting noticeable advantage. In the other case, you are not getting any advantage, just random. But when you take the average of these two cases, you will end up getting noticeable advantage. Right? So C is indeed now an algorithm which it's a single algorithm which distinguishes with noticeable advantage. But the last part of the question allows you to do prediction, which is a slightly different definition compared to computational indistinguishability. And then in the class, we actually showed that these two definitions are equivalent. Computational indistinguishability implies prediction indistinguishability and vice versa. So if you have an algorithm that can break computational indistinguishability, you also have an algorithm which can predict with probability noticeably better than half. So this is a very simple idea which allows you to skip sort of ugly probability calculations. Okay, so let's quickly go through 6 and 7 as well, right? So in problem 6, you are given a public key encryption scheme, and you have to design a key exchange protocol using that. I think most people got the idea correct, but some of the people, some of you didn't really give any proof of security. So here we have Alice and Bob. What we can do is Alice can generate a public key and secret key pair and send the public key to Bob. Bob can sample a key at random. Let's say L is supposed to be the length of the key, or maybe N. Then Bob just encrypts the key with the given public key. And And then Alice can just decrypt the ciphertext to recover the key K. Now you look at the adversary sitting on the channel who is watching. What does this adversary learn? Adversary learns the public key and adversary learns the ciphertext. Intuitively, given the public key, you have no idea what the ciphertext is. So good, it's a very simple protocol. And now let's try to prove the security. Proof is also fairly straightforward. The first thing which you need to realize is, so there's an adversary Eve sitting on the channel. So view of this adversary Eve is just the public key and the ciphertext K, which is also the protocol transcript tau. What do we need to do? We need to prove that K and so this is the transcript, this is our public key. We need to be able to replace the key with uniform. Okay. And unfortunately, here in this distribution, the key K, even though uniformly generated by Bob, is not uniform, right? Because you're also given an encryption of this key. So I think there's a question about the last. Yeah, we'll come back to that. So let me write down the full distribution. And here, K is coming from the uniform distribution. And of course, the PK and SK are coming from the, the right key generation algorithm. But let me skip that part. So this is computationally indistinguishable from K, PK, now I change the encrypted message to K prime. Okay. Actually, I can just change it to 0. Or should I change it to K prime? Yeah, let's change it to K prime. Where both K and K prime are uniform strings, but independent and random. Okay. And here, this is the same as U of K. Okay, so here already, if you look at the key and the transcript no longer has any information about the key, and key is sampled uniformly at random. And this step is basically just rewriting the same thing in a different way. And this is exactly the definition of key exchange. Okay, any questions? So now let me look at problem 7. In problem 7, you are given a public key encryption scheme, and you have to use that to build a one-way function. This is slightly tricky because one-way function is not randomized. It's a deterministic algorithm. The input of the one-way function determines this output entirely. On the other hand, if, for example, you try to encrypt or something like that, that's going to be randomized. Okay. But nonetheless, easy idea. I can define my one-way function f of x as follows. Interpret x as a random string, which of course it is. In a one-way function, your input is a random string. Run the key generation algorithm. And this will give you the secret key and the public key. You throw away the secret key, you output the public key. Okay? Why is this one way? So first of all, let's just verify that this is indeed deterministic. It is, right? So you're running, let me clarify, this is not key generation with x as the security parameter. Rather, let me write it as in a different way. This is the key generation algorithm where you use x as the randomness, as the random tape. And once you decide the random tape, the key generation algorithm essentially becomes deterministic. Why is this hard to invert? Now, given pk, can you compute x with noticeable probability? Any ideas why or why not? Well, you cannot. The reason is that if you have x, you can actually recover a secret key and the public key from that, right? This means that if you can compute x, you can compute the secret key, which means that in your public key encryption algorithm, given the public key, I am able to compute the secret key with noticeable probability. And that just completely breaks the security of the public key encryption scheme. If I can compute secret key from the public key, I can just decrypt any message. Okay, let me get back to the question which was asked. So there seems to be one more question. What if you find an X with the same public key but with a different secret key? Yeah, that's still fine. Anything which is encrypted under the public key pk can be decrypted using any secret key which is valid corresponding to this public key. And this follows from the correctness property of the public key encryption scheme. Okay, so you are asking, there was a question, you have g to the power b on the left. Well, for this, I'm just claiming that this distribution d1 is indistinguishable, or it's the same as the distribution d2. The left part doesn't really matter. And then I will apply the transitivity of computational indistinguishability.
But like you can do it without the Ddh assumption.
Yeah, because again, forget about this distribution. I'm just looking at this distribution, and I'm looking at this distribution, and I'm trying to see if they are different or if they are the same, right? In distribution D1, I was generating some random number B from ZQ. And I was computing g to the power A to B. But you look at the remaining values in this distribution, B is really just uniform because none of the other values depend on it.
Right. Thank you, sir.
So what is A2 times random? It's also random.
Random? Yeah.
And I'm just calling that random number R2 here. And then I can look at the left side. I can say that, yeah, this is indistinguishable from this. This is indistinguishable from this. And the rest follows from transitivity.
Thank you, sir. Thank you.
Okay, good. So we will stop here. I'm still around for a few more minutes.